two out arrows, and that they were actually interested in finding what physicists call the partition function as a way of calculating the energy. So you put a certain weight at each of the vertices depending on the configuration at that vertex. You take the product of the weights, you then sum over all possible configurations, and then you do a limiting process as the size of the alternating sign matrix approaches infinity, and you see what you can say about that partition function. But the kinds of tools that they had developed, Greg Cooperburg realized could be used to study this problem of counting alternating sign matrices. So I'm going to call a vertex a horizontal vertex if I've got two in edges coming horizontally. That corresponds to my +1. I'll call it a vertical vertex if my in edges are coming vertically. That corresponds to a -1. And incidentally, once you know where the horizontal vertices are and the vertical vertices are, you know where all of these green jigsaw pieces are located, so that completely determines your 6-vertex model. And I'll call the others southwest, northwest, southeast, northeast, depending on where the arrows are coming from. There's certain natural parameters and weights that we want to put on a 6-vertex model like this. We'll let capital N be the number of -1s for this particular configuration. N is equal to 2. And the alternating sign matrices are a natural generalization in many respects of permutation matrices. And there's a natural way of defining the inversion number for an alternating sign matrix, and one way of defining it as the number of -1s plus the number of southwest vertices. If you actually just simply take a permutation matrix, translate it into a directed graph such as this, it'll be a directed graph without any -1s. It'll be a 5-vertex model. And in that case, the inversion number of the permutation is just the number of southwest vertices. And then we'll also put a weight on each of the vertices, so we'll designate a vertex by a pair of variables. This is in the 2nd column and the 3rd row, so we weight it by x2, y3. And in the 1980s, Anatoly Etserkin and Vladimir Korepin came up with a remarkable determinant identity that's given here. Actually, they didn't come up with this. They came up with comparable determinant identities for other boundary conditions, but they mentioned that it would be possible to set it up with the particular boundary conditions that you get in the case of alternating sign matrices, and they left it to Greg Cooperburg to actually work out the details of this. But what we have on the left side of the equality is a determinant. So we're looking at an n by n determinant in 2n plus 1 variables, x1 through xn, y1 through yj, and an extra variable or extra parameter a stuck in there. We're multiplying this determinant by that product over all pairs I and j. So that's going to turn this determinant into a polynomial in the x's and the y's. And it's going to be an alternating polynomial in the x's and an alternating polynomial in the y's, since the determinant itself is an alternating function of the x's and an alternating function of the y's. And that means that this polynomial that you get when you multiply the determinant by that product is going to be an alternating polynomial in the x's, alternating in the y's, which means that we can divide through by the van der Waals products in the x's and the y's separately. And that gives us a symmetric polynomial in the x's and a polynomial that's symmetric in the y's. So the left-hand side, trivially, is symmetric in the x's, it's symmetric in the y's. You can do a simple counting and see that it's a polynomial of degree n minus 1 in x1. And as we'll see later on, once you're working with polynomials, life is wonderful. Because if you've got a polynomial of degree n minus 1 and you want to establish an identity for it, You only need to check its value at endpoints, and you've got it. By induction, the left-hand side and the right-hand side are equal when x1 is equal to y1. Well, basically what that does is it simply cuts it down from the n by n case to the n minus 1 by n minus 1 case. And in addition to that, I know that the left-hand side is a symmetric polynomial in the y's, so if I know its value at y1, I know its value at n points, y1 through yn. If I can show that the right-hand side is also a symmetric polynomial in the y's, I'm done. So that's almost the complete proof of that determinant identity, and this completes it. Baxter's triangle-to-triangle relation. So Rodney Baxter, not this Baxter, another Baxter. This is Rodney Baxter. He's at Australian National University, but that picture was actually taken in New Zealand. He had, back in the 1960s, actually established a result on corner transfer matrices, commutation of certain corner transfer matrices that implied that the right-hand side is a symmetric function in the y's, and that does it. And once you've got this determinant identity, you can specialize it. So here's a list of the variables, the specializations that turns the right-hand side for a suitable value of z into a constant times the number of n by n alternating sign matrices. The left-hand side gets a little trickier because if you try making these substitutions, you wind up with a very singular determinant. So you've got to kind of sneak up on those variables. You can't just plug them in. But you can do that sneaking up. Greg Cooperburg figured out how to do it, and the left-hand side collapses into precisely the product of factorials that you want. And so that's the proof. Very simple, very direct, but using some pretty high-powered physics. Same year, 1996, Doron then took this idea of using the Koropin and its Zirkin determinant formula to prove the original conjecture, the refined alternating sign matrix conjecture. And in some sense, the story was over then, and so that's when I started writing my book to tell this story, and the last chapter outlines Doron's proof of the refined alternating sign matrix conjecture. But of course, that wasn't really the end of the story, that was only the beginning of the story. People have begun to find lots of connections between these alternating sign matrices and other types of structures. And so now I'm going to move past where I finished the book in 1999. There are a lot of directions that people have headed. And I want to just pick out a few of them that I think are particularly interesting. One of them deals with a question that Richard Stanley posed to Dave Robbins back in the early 90s. I think Richard may have done some exploration of these alternating sign matrices. And he suggested to Dave Robbins that you might want to look at alternating sign matrices that satisfy various symmetry conditions. There appeared to be some nice formulas there. And that's the book. 2001, Greg Cooperburg began to prove these formulas. So the first of these deals with vertically symmetric alternating sign matrices. So an alternating sign matrix that's left unchanged if you do a vertical reflection. And there's a nice formula for counting these. Cooperburg also was able to prove Dave Robbins' conjectured formula for the number of half-turn symmetric alternating sign matrices. So they're left invariant if you rotate them by 180 degrees. There also is this formula for quarter-turn symmetric alternating sign matrices. They're unchanged if you do a 90-degree rotation, and I love this formula. It's been verified, but nobody has any idea why it has this particular nice form that it does. That the number of quarter-turn symmetric of a 4n by 4n matrix, you take the number of half-turn symmetric alternating sign